Good afternoon, everyone. I hope you really enjoyed the 4 presentations on color, but let me slightly change the topic and maybe it will interest you. So today I will discuss about magneto-optics and its response on all dielectric gratings. So what is magneto-optics? I won't be diving too much into this subject, but when an incident light interacts with a magnetized magneto-optical material, in reflection or transmission, we observe phenomenons, basically like polarization rotation effect or intensity modulation effect. So the intensity get modulated. So my work is primarily on this effect of intensity modulation, and it is known as TMOC, that is transverse magneto-optical curve effect. I will discuss it about later. But before discussing it, I will discuss about the device that we fabricate so we can use this effect. That is called guided mode resonance grating. It's a complex word, but I will try to explain it. It is a grating deposited on a waveguide that is further deposited on a substrate. Now, suppose we have an incident light. What happens? This light interacts with this grating. It gets diffracted into the grating. And when it gets diffracted, if the propagation constant of the diffracted light is equal to the waveguide, the light gets coupled inside it, according to this equation. Oh, sorry, this equation. Now, what happens when light gets coupled inside, it starts propagating. At certain point, this light gets destructive interference with the incident plane waves, and we go to dip in the transmission spectrum. So this is how we observe. Now coming back to the transverse magneto-optical curve effect. So what is this effect? It is a relative change of intensity that is reflected upon the magnetization reversal. So suppose I have a magnetization field, and when I reverse it, we see a change in the reflected intensity. So let's suppose I have a propagation equation in TM mode. I don't want you to focus on the equation. What happens when we introduce magnetic field? We introduce an off-diagonal permittivity terms. Now you would be asking, what is this? I don't understand. Well, let me tell you. Suppose we apply a field in our material plus M. It will originate an permittivity term plus epsilon MO. If I reverse the magnetization, I have minus epsilon MO. Now what happens if I put these two values in these two equations? We will have a change in the propagation constant. Now what happens when we have a change in propagation constant? Well, according to the coupling equation, if we have a change in propagation constant, we have a change in the wavelength at which our system resonates. Now what happens is at a certain wavelength, if I have a delta lambda, I have a change in transmittance, or I have a change in reflectance. Now this change will result in the modulation of intensity, and it is plotted something like this. And it is given as a relative change. So this is the basic mathematical formulation. Now, the detection of this effect is very, very low. It's around 0.1% till there was a work done in laboratory Hubert Curien. The work was to introduce magnetic nanoparticles inside the magneto-optical film. The magnetic nanoparticles has a concentration of 26% that was embedded in silica matrix. And that improved the result from 0.1% to 12% for a certain angle of incidence. This was quite phenomenal. So my work was to seek out if there is any further possibilities to improve this effect. And there was an idea. What was the idea? It's to work near the cutoff thickness of the films. Cutoff thickness are the thickness below which we will lose our guided mode. So we have to be careful. So what's the idea? If I decrease the thickness of my magneto-optical film, as you can see here, the full width half maxima of the transmission curve decreases. Also, the amplitude of my curve increases. This results in a greater difference in transmission and reflection, and hence the greater TMOC values. But I have to be careful in designing various parameters. So I had two approaches. My first approach was to introduce a layer of tantalum pentoxide between the magneto-optical film and the glass substrate. Why I do this is because to increase the difference of refractive index between the cover and the substrate. Now, it's a very well-known rule in optics. If we increase the refractive index difference between cover and substrate, we increase the propagation constant. And if you resemble the coupling equation, I said if I increase the propagation constant, I can enhance the Timok effect. So this was the basic principle. Also, by this layer, I can confine more magnetic field inside my magneto-optical material, and by confining more magnetic field, I can further enhance Timok. It's a double-edged sword. It will take time, so I will not discuss about that. Now I optimize my structure according to this parameter. And as we can see, we have quite drastically improved the Timok response. Like we are getting a Timok in reflection around 58% for a very good detection. So we can see we significantly enhance our response. But you must be asking, if you are going to increase the difference of refractive index, why you just can't increase the refractive index of the magneto-optical film itself? Well, I can, and this was my second approach. I just increased the difference of refractive index by increasing the refractive index of the magneto-optical film itself. And we try to observe by varying the thickness of the magneto-optical film if we can enhance it or not. We have to be careful while designing the parameters. Now these curves might look, what is this? But let me just focus on the results as of now. As you can see, when I vary the thickness of my magneto-optical film, I get a transmission dip very nice and a very good value of Timok in transmission. Same, I got a very good value in reflection. And hence my job was to optimize the structure. So for this particular thickness, I got very interesting results. And as you can see, these were the original results that were published in Laboratory Hubert-Curien, and these were my results in simulations that I did. And you can see that the reflection we are observing is 19%. So if we use these structures in magnetic field detection and sensing, the sensing would be really nice. As you can see, the improvements is there. So we can easily sense, and the Timok values is also very nice. So if I compare both the two approaches I did against the work originally done in Laboratory Hubert-Curien, I think my structures are quite promising. I tried to do some experimental verification with some structures, and the results were quite satisfactory, but for all of my structures, the fabrication was still pending, and the results are still yet to be verified, but it definitely looks quite promising. So that's all from my side. Thank you very much.